let's consider this definition of a periodic function. We already know this, but let's just see once more. D is a subset of the set of real numbers, and f is a real valued function with D as its domain. Then f is said to be periodic if there exists a positive real number R such that for all x in the domain D, x plus R is also in D, and the values of the function at x and x plus R are the same. And if there exists a smallest such R, which we are calling P here, which is also positive and for which those same conditions are true, then P is called the period of f. In another terminology, for any such function, any real number R which is positive and satisfies these conditions is called a period of f, and in that terminology this P will be called f's fundamental period. We are, however, not calling these things period. We are only calling any smallest such P the period of f, if f is periodic. Okay. Now we already know many examples of periodic functions. For example, the trigonometric functions. Say your familiar tangent function. Let me call this example 1. I am choosing the tangent function because the tangent function does not have the entire set of real numbers as its domain. So this condition that for all x in the domain, x plus R should also be in the domain is not trivial in that case, in case of the tangent function. So consider this function. You know what the domain of the tangent function is. You can take all real numbers except the odd integer multiples of pi over 2, because at those points cosine becomes 0 and tangent hence is undefined. So the domain here is this. From the set of real numbers, we remove those points. And f of x is of course our tan x. Is this function periodic? We know it is periodic because we know this fact. For many values of R, one of those values for the tangent function is pi. Tan x plus pi is also equal to tan x for all x belonging to this domain, which is something that we already know from trigonometry. But what is often overlooked is this condition. Is this condition true for this D? And say in place of R you have pi. Let's see, okay. Pi, of course, as a real number, pi is positive. So you can think of pi in place of R. Let x be any element in our domain now. We want to prove that x plus pi is also in this set. Now x plus pi of course is after all a real number. So for that to be in this set, it should not be in this set. Suppose that x plus pi is in fact equal to this. for some integer n. Then what happens to x? X is 2n plus 1 times pi over 2 minus pi, or 2n plus 1 times pi over 2 minus 2 times pi over 2. So if you take pi over 2 common out, then you get 2n plus 1 minus 2, or 2n minus 1 times pi over 2. But then this again is a number of this form. Why? Because this is 2 times n plus 1 minus 1 times pi over 2, where n plus 1 of course is an integer because n is an integer, but this is not true, because according to our choice of x, x cannot be a real number of that form. So that means our supposition is wrong. Hence, x plus pi cannot be in this set. So, x plus pi belongs to the original domain. Also, from elementary trigonometry, we know this: tan x plus pi, which is our f of x plus pi, is equal to tan x for all x belonging to this set. And that is why this function, which is just our tangent function, is a legitimate periodic function. Moreover, again using elementary trigonometry, one can show that pi is in fact the smallest such r. In other words, for this function, pi is p. Okay, so this is a periodic function whose period is pi. No other smaller positive real number than pi will have this property, that tan x plus that number is equal to tan x for all x in this set. Okay, so these are pretty standard things we already know. But next let us see an example of a periodic function which has no period. It is periodic, but it doesn't have a period. Or in that other terminology, it is periodic and has periods, but no fundamental period. So next, consider this function f from r to r, f of x equal to 1. The constant function 1. So in this case, d is r itself. So obviously, the condition that x plus r belongs to d for all x in d is going to be trivial here. But what is our r? Let r be any positive real number. Clearly, x plus r belongs to the domain for all x in the domain. Also, f of x plus r is, after all, it's the constant function, so this is 1, which is also equal to f of x. Hence, f is periodic. But because we have proved that these conditions are true for any positive real number r, so no such smallest positive r exists. If you choose a smallest positive p, then you get another smaller one, p divided by 2. If you think that is the period, no, there is another smaller one, p divided by 4. So there is no smallest positive. Since the above conditions are true for all r greater than 0, no such smallest number exists. Thus, f has no period. A periodic function, but that does not have a fundamental period.